All right, welcome everybody to another week of how to coding smart contract of Bitcoin. And last week, for today, we continue the last topic, which is zero knowledge on top of Bitcoin. So last week we briefly talked about what is zero knowledge, and specifically what is one type of zero knowledge we call it ZK snark, and why it's suitable for the blockchain space, because so-called is the proof size is small, and also the verification is also very computationally light. So we also run a few use cases, for example, Mixer and Zcash, and also enable new kind of a so-called hidden information game, right? So in this week, I think last time it was almost like a theory and also hypothetical use cases. So in this week, I'm going to dive into a little bit details and so-called get hands-on a little bit and see how exactly you can do zero knowledge on top of Bitcoin. Okay. So before I dive into detail, it's great to have people review this slide a little bit, because this is what the tools we're using today is pretty much going to follow this diagram here. Okay, anybody here will be around last week? Just try to briefly summarize what is going on here. Anybody? Domingo or Liam, you want to have a try?
Yeah, can do. So it's I think one of them, the top one, is the one that's passing in. Sorry about that. I think the top one is passing in a private key and a public key, isn't it? And a value that's going through a function and returning something, a proof. No, that's the second one.
Yeah.
The first one is creating the key. Yeah.
Yes.
The second one is creating the proof, and the third one is passing the proof and the public key to the what's it, the verifier or
verifier.
Or,
yeah, verify. Yeah, sounds about right. So just give a brief recap. So here, this when you're using ZK snark, usually it runs in 3 steps, and the first 2 steps, they are in our context, it runs off chain. So basically you do it off chain. So you have a setup. You basically, there's a function you want to prove, can be arbitrary function you want to prove, and then you add a little bit of randomness, you get a pair of keys, the proven key and the verification key. Okay, the difference with Bitcoin keys is the key pair, the private and public. In this case, both must be public. Okay, I mean, when I say public, meaning but known to both approver and the verifier. Okay, so then once you get the pair of keys, you got the secret value, and which also usually called a waitlist. That's why it's W, and also public input. Then the prover can generate the proof. Okay, and once you have the proof, you can hand it to the verifier. The verifier, without knowing the secret, so also called waitlist, he can, and with a proven key and public input, he can check whether this proof is valid or not. Okay, so this this is like a generic workflow for all the ZK snarks. So we are going to look at some tools that can realize these 3 steps today. Okay, so there are many different types of tools, and for us, today we mostly focus on this tool called Socrates. So as you can probably guess, this is like a wordplay on Socrates, but then it's replaced with Z and zero knowledge, right? ZK. So this is some tool originally designed for Ethereum blockchain, but because the zero knowledge attack, right, is a platform or blockchain agnostic. So we kind of adapt it a little bit and then make it also run on Bitcoin as well. Okay. So basically what this is Socrates basically is a tool to generate and to running zero knowledge, specifically ZK snark on usually on public blockchains. Okay, so it does all the 3 steps we have seen before. So if you come back here again, right? So you kind of need all the 3 steps, right? And also you need a way to represent what your function is, right? Because you know is this function usually is some kind of program. You can think of some kind of program, right? Whoever is trying to generate the proof or agree to verify the proof, they have to agree on what the function is. So they need some kind of representation. And for Socrates, so basically they have it's a tool, but it's also its own language. So it's a little bit like Python-ish if for people who have known Python. So this is also called a domain-specific language. So it's you can see if you're seeing Python or any kind of JavaScript code, this should be familiar. This is the next thing we're going to. But before we dive into like almost like a code, we need to get a little bit of almost like a high level overview, so you understand what the code is doing next. Okay, so I think this diagram, yeah, it seems a little bit verbose, but let's dive into it. So and then always keep in mind of this diagram. So then you're happy to understand what is going on here. Basically, is the implementation of the algorithm zk-snark there. So first step, right, that I just showed a little bit earlier. So you have to, before you do anything else, you have to tell Socrates what's the function you want to prove, right? So basically this, you write a little bit of like a Python-ish code to represent what is your function you want to prove. Maybe you are trying to prove, x, hash to y. So x is a preimage of y, or you want to say, this public key corresponds to this private key. So you are doing some kind of elliptic curve, or you are just saying, oh, I want to prove I know, let's say solution for a given Sudoku problem, right? Or any kind of a computational problem you can think of, right? So first step is you have to code the function, in this high level language, and then the language is going to compile it. We don't worry about this. It's going to pretty much just compile to like the language that zk-snark can understand. So we don't have to know what it is, but you can think of it's like any other high level language, right? It has to be compiled, and then once it's compiled, it has 2 branches. One is this is setup, right? So this is the setup in the zk-snark, the first step, right? So you take a function, right? Pretty much you take the function and you have a little bit of randomness and here. So you generate the pair of keys. You see the pair of keys here, right? The proving key and the verification key. Okay. So what's the second step then? So once you have the function, you generate the so-called witness. You run a computer witness. Witness is just a secret value to the function, right? The little w in the previous slide versus the public input, which is x, right? So basically here, once you have the, usually this is called a circuit in the ZK language because this is the native language for zk-snark. So, but we don't have to get to the detail. Basically, you can think this is usually why people call this circuit. So once you have a circuit, basically you have the function, you can compute the witness. The witness is just the secret value. You have to compute it because a lot of time it's based on some input. You have to compute it. For example, it could be like a solution to some Sudoku problem, right? So once you have given all the known grid, but then you have to run the Libby program to compute it. So once you have the inputs, secret and public, and you have proving key, right? So you can generate a proof, right? This is the second step in the zk-snark, right? This is the proof. So once you have the proof, you can give it to the verifier. The verifier has a verification key, so you can check whether this is good or not, right? Make sense? Does this, yeah, pretty much this is implementation of the zk-snark. Any question here? I think this is quite a slide and a lot of information. Want to make sure everybody is on the same page before we dive into the code.
So you give the proof to the verifier at the same time as you give, because it's not on the It's not on this diagram, is it? That you actually do anything with the proof, the program result.
Oh yeah,
The proof.
basically once you have the proof, right, you can give it to the verifier. The verifier can using the verification key and say whether the proof is valid or not, running the verification algorithm from zk-SNARK.
Okay.
Yeah, it's not shown here. This is basically show all the how do you generate different things here.
Okay, yeah.
Any other question?
I think it'll be clearer if we have an example, a simple example or something.
Yes, that's what we are going to do next. Yeah. Don't worry about it. Okay, this is exactly what is going on here. So this is a concrete example. And this also, I could say, is a useful example. So a lot of time, right, when we're dealing with cryptography, especially let's say Bitcoin, right? So that's a so-called, factorization, the hard list of factorization. Basically, if I give you a very big number, which is a multiplication of two numbers, prime numbers, right? If I just give you the product, is computationally almost impossible to know what are the two factors are, right? So let's say equation, right? I give you n, which is two numbers, p and q times together. And this n, if it's very big, let's say 256 bits, right? And these two are prime numbers. Then it's almost impossible if I just give you n for you to know p and q. But the opposite way is very easy, right? If I have two numbers, I can just multiply it together and give you n, right? So this hard list is a lot of time is the biggest, our kind of a protection against attackers. So what if, let's say, somehow I just want to, I give you this n, and then I want to prove I can factorize this n. But here's what it gets tricky. But I don't want to show you the result, right? So this plays into the zero knowledge proof sense, right? Because I'm telling you, I know these two numbers multiplied to this given big number, but I don't tell you which these two numbers are. Okay, so this is the proof we're trying to generate here. So as you can see, the first step is to, you have to. This is a function we want to prove, right? And then you have to, represent it in a so-called zk-SNARK way. Using Socrates, basically you're using this kind of like a small Python code of this form. Basically, you have a main function. It's like many other mainstream language. You have the main, like C++ or Java, whatever. And then you declare using this as a type. Basically, this is a field. I think we are not going to get it detailed, but you think about this like an integer. Right? So integer type for these three numbers. But then the key here to note here, that's qualifier here, private. Okay, so this is the so-called if there's no private in front of a parameter, it's going to be public by default, right? This is going to be the public input. So all these three are inputs, right? And then if you declare private, it's going to be secret. It's going to be a part of the witness, so-called. Okay, so basically this says it's pretty readable, right? So basically I know there's two secrets. If you multiply them together, it's going to be this public number n, right? But I'm not telling you these two numbers. And also, you want to prevent the degenerate case, right? I don't want you to give me 1 and n times this. So it's always 2n, right? It makes sure it's actually factor, so it has to be larger than 1, right? So in this way, I'm proving you I know the two factors of this big number. Make sense here? It's pretty readable?
Yep.
Okay. All right. So that's the first step, right? So is corresponding to here. Basically, you write the high-level code, and then you compile it, right? So let's go back here. So you can install here Socrates. I'm going to put a link so you can go there and you can download it and play with it today. So you say Socrates compile. Once you compile, you pretty much get a so-called circuit, right? But we don't have it. Just some zero-knowledge format. Yeah, people usually call it circuit. So once you have a circuit, you can set up, right? So the setup is step 1. Then you get a pair of keys, right? Once you set it up, you get a pair of keys. See here? Right? Now we're here, set up. Once we finish first step, we have this flattened code. You can think of it as a circuit. Once you have circuit, you can set it up. You have the 2 keys. Once you have the 2 keys, you can so-called. Once you have, you can, and then this is a separate thing. Then you can run the program. Basically, you run this, you give it all the numbers, and then you can compute something called witness. Okay. So witness is something here. Okay. You compute witness. So once you have witness, you can generate proof, right? With a proving key. So that's what it does here. You can generate a proof. Okay. So once you have the proof, you can ask the prover, the verifier to verify it. Okay. You can run verify. Okay. So if everything matches here, the verifier is going to say yes. It does. The prover does know the secret 2 numbers which times together equals to n. Okay. If not, it will reject it. Okay. So, and then you may ask, yeah, you just show me everything, but what is relationship with Bitcoin then? Yeah, this is good. This is the right question, because so far we've not covered anything about Bitcoin, right? But here's the thing, as I said in the ZK Snark slide, ZK Snark is very friendly to blockchain because the proof is very small, and also the verification is also very lightweighted. So that's why you can generate the verifier. For us, we always talk about ASCII. So basically, you can run. We can pretty much like augmented the Socrates. So we add this command. So then you can export the verifier. So verifier is a algorithm, right? You can run off chain, and then if you want to run on Bitcoin, you can just add this command, run this command, saying Socrates export verifier. That's ASCII. So it's going to export the ASCII file that can do the verification, and then you can use this to this library file, right, in your smart contract. For example, you just want to say, hey, whoever I publish a big number, whoever knows these 2 numbers, they can take the money, right? You can say this logic, or you can say, oh, not only this guy has to know these 2 numbers, but also this number has to be also has to know some hash per image, right? You can combine it with, once you have this primitive, right? This is the library, and you can then integrate in your program, in your smart contract, and finally your app to do anything you want using zero knowledge. Make sense? Does it make sense here?
Yeah, but
That's
how does the verifier know that the proof is for the right thing?
Oh, that's what the okay. So I think very good question. Basically, when you export it, you pretty much the verification key is pretty much hard coded. It's going to be part of the code. Okay. So verification key is, you can almost like think about a hash of the function. It's very short, right?
Yeah.
But you can almost you can think about it almost like a digest or hash of the program. So you can be sure, because the verification key is hard coded in verifier, so you can be sure you are not proving, let's
so
say,
you know that it's that program is
problem.
running. But if I were to say I want to, you have to, n has to be, say, 91. How do I know that n is 91 and he's not just calculated another prime number?
Oh, this thing, because it's public, right? So this is, you think here, there's no private
so I can see
qualifier.
that.
So that's 91. It's also going to be part of the here because it's public.
So I can look at that and I would see that 91 there.
Yes,
somewhere.
you can see this because it's public. That means the verifier also knows it. So here, I'm going to even show you one concrete example. Basically, you not only, let's actually just go there directly. Let's say, I don't know whether, can you see my browser here?
Yeah.
Oh, you see the browser, right? Okay, cool.
Yep.
So
Yep.
basically, this is the first link. So this is more concrete, instruction. Basically, I see here you install it, right? Once you have installed, I just show the example I show you in the slides here. So you can compile, set up, calculate with this. You can generate proof. So just want to give you a sense of what the proof looks like. This is what the a proof looks like. So here you have the inputs, basically all the public inputs, right? So for example, here I use 91, I guess. So this is the hex for 91. You can check later, but then you have the proof. Yeah, the proof is almost like its own structure. But we don't have to go to the details, but it's a bunch of like points on the elliptic curve. Basically, that's what it is. So this is the proof. Once you proof, you can export the script verifier. So the verifier actually, you can, if you want to get a sense, it has the 91 into it, the public input, but also the verification key. Do I have the verification key here? I don't show the verification, but yeah, it's everything. Both the public input and also the verification key is hard coded in this, we call it script,
Yeah.
verify script. So that's what it binds, right? It binds to the program you want to prove. You cannot cheat because both are hard coded there.
Yeah.
Okay. Then you can import it as just any other library. And then you can call this, this verifier to make sure it's good. So you have the proof, but also you have the public inputs here too. Make sense?
Yeah. Yeah. Excellent. So, thanks.
Yeah, let's want to give a sense. Okay, yeah, this is the proof. Okay, yeah, this is how I show you how you can deploy it and run it on Bitcoin if you want to get a really hands-on. Yeah. Okay. Any other question? Okay, good. Let's go back. So I just showed you the concrete example. This is like the workflow for any, if you want to prove any, function using the zero knowledge proof. Okay. So then once you have this tool, I think probably you have not realized the importance. Basically, now you can create zero knowledge for any arbitrary computation problem and then verify it on Bitcoin. Right? Then for all the examples I showed earlier, you can run this. You can have this. You can prove. Either is, let's say, I just give a few examples. You can run zero cash. You can, if you really want, you can implement Zcash on top of Bitcoin because, at the bottom, the Zcash tech stack, right? It's just zk snark. Or if you want to build some kind of mixer, which I don't strongly recommend, but I'm just telling you that it's technically possible today. You can use the tools, Socrates, you can actually run it on Bitcoin today, okay? And also you can build all kinds of like zero knowledge games, okay? So yeah, this is a very powerful, basically any zero knowledge you see around, in other blockchains or even, let's say, entire cryptography. If you want to use zero knowledge, specifically zk-SNARK, you can actually deploy it on Bitcoin today. So I just want to show you something. Go ahead.
I was going to say you can use so you can use this in the script for the unlocking script, but you would still be able to see the value, wouldn't you, of the outputs?
Oh, you only see what's open there, right? For the public ones, you never see this because this never shows up here in plain text. For verify on chain, right? You only see this and also the verification key. Make sense? So all this is always hide from the public. Only the prover knows it. So that's the amazing part, right? The prover doesn't show this too, but somehow you are convinced, oh, he knows this. He had these two numbers tapped together equals and had this bunch of properties.
Oh, right, yeah. I meant if you had if you had an input of say, I don't know, 5 satoshis, you couldn't hide that, could you? At
Oh
this
no,
level.
no, no,
Yeah. So it
not
can't,
this level.
no, which is what Zcash does, doesn't it? That hides also the amounts.
Yeah, yeah. And then you implement it almost like a sub currency, right? Kind of like a token, fungible
Yeah, on
tokens
top
on
of
top
it.
of
Yeah,
it,
yeah.
right? And
Yeah,
then you
token.
don't use Satoshi to represent the amount of Zcash, let's say Zcash
Yeah.
tokens, right? So in that sense,
Okay,
you
yeah,
can
yeah.
hide. It
That
pretty
makes
much
sense.
is
Yeah.
like it's all private, right? So in that sense, you can you can do anything you want. It's
Yeah.
programmable. So okay,
Thanks.
yeah, good point. So since we're already here, so we have this website called from ascript.io. So it's called add and learn on top of it. So basically, this we have we have the tic-tac-toe, which is the traditional non-zero knowledge, but I also have this thing, which is very cool. I think it's strongly recommend to go through this. This is I think the world's first, not only the first. I think they're the only one that's a ZK zero knowledge proof, interactive course, right? So basically, what it is assuming you have no prior knowledge about zero knowledge, is specifically ZK Snark, then you go through this course, you have all the interactive parts. Basically, you can not only show you, what it does and what it is, but also, have the code also available. You see the Zoc for Socrates. So basically, this is a battleship. I want to prove to you, right? You guess a point. I'm telling you whether it's a hit or miss, and I cannot cheat. And also, I can hide the position on chain, right? Because if it's on chain, and your opponent knows where the fleet is, then it's not ZK ship the game, right? So basically, it's a zero knowledge version of the battleship you can play on Bitcoin today, and you can code in Socrates. So this also show you all the code. So once you're even finished, you can actually deploy all these things to Bitcoin. And then the best thing is you can also hook up it with some kind of front end, so you can actually click around and see what it look like. So yeah, I think this is the best tutorial for zero knowledge. If you want to just build some kind of a game on Bitcoin, walk through this course and then you can build your own game. I showed ZK Snack based on Battleship, but you can do anything. Sudoku, or if you are really into it, something like Dark Forest. Yeah, any kind of game, or poker, or anything you can think of. You can, once you have this template, pretty much you can just swap out your own circuit
Yeah.
or your own front end. You can build your own game today. You don't have to wait for 18 months or somebody to change the Bitcoin protocol or anything. Okay. Yeah, strongly recommend you if you are interested in any kind of zero knowledge, specifically on Bitcoin, walk through this course. I think you will get a very good understanding of what it is. Very hands-on. You can see all the steps, and eventually you have even. I think it's a linked here. If not, yeah, it's linked somewhere in this course. You can even go to the source code for everything, not only for the circuit, but also for the contract, and also for the front end, how do you connect to the wallet and then play it here on a web page. Okay. All right. Let's come back a little bit. Okay. So I just showed you, how do you do, the generic workflow. How do you do this on Bitcoin, right? So you have around all this bunch of steps, and then if you want to get very close to the code, I just recommend that course, ZK version of Battleship. Run through it, and then you can get a very good idea, and then you can, change it, adapt it to, implement any kind of zero knowledge you want to have on Bitcoin. So here to close this up, I just want to mention a few things. Why, why do you want to do this on Bitcoin versus, I heard that you can do this on Ethereum, on Zcash, on, a bunch of other blockchains, right? I'm here just to say, actually not only Bitcoin is good, and actually it's the most friendly zero knowledge protocol, for a blockchain for zero knowledge proof. Why? Because first of all, it's scalable. because even you can do the same thing. You can code, you can verify the same. You remember the verify, right? So basically, it's a contract you can deploy. It has a cost, right? Because the verification algorithm, right? It's like a digital signature verification, right? It's not it's independent blockchains. So in theory, if you have any kind of smart contract capability, you can program this on any blockchains. But here's the trick, right? Because other ones they're not scalable, so it's going to be very expensive. For example, you verify this factorization of a big number, it may cost you like $10, okay, on Ethereum or other blockchains, right? Versus if you do it on Bitcoin, and we have optimized to it to like I think it's around a little bit over 1 megabyte, so it's about 1 cent. Right? Think about the cost. Right? I think we can push it even smaller. But even given what's available today, you can verify the same thing either using $10 or using 1 cent. Right? I'll let you be the judge. You want to spend $10 to verify one proof, or you want to spend just 1 cent? It's the same thing. Okay, and 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 because of this, there's another big advantage we have. So we can actually, because I just hinted before, right? There are not only one way to do zero knowledge, right? For example, this zero knowledge. Anybody heard about the Bitcoin curve, like SECP 250 K1? Anybody heard about this curve before?
Yeah.
So-called Bitcoin curve, right? So again, as I mentioned, zk snark also runs on some kind of like a elliptic curve, but it's not the Bitcoin curve. Yeah, usually it's called a BN 256. So here's the problem. For Ethereum, you can only support one curve, right? It's hard coded there. Because otherwise the cost is going to be like not $10, maybe $1,000 or even $10,000. Okay. They kind of cheat. They add a new opcode pretty much, right? It's like check data sig or whatever. Now, whenever they run into issues, they need to add a new opcode to pretty much subsidize what they're trying to do for zero knowledge. But the drawback is it's hard coded into the protocol level. It's like opcode, right? But then if some new curves come along, they cannot, what if I have some new curve better, right? Better security or more performance, and then they cannot change, right? Because, you you and me now, we have been with Bitcoin, you know how difficult it is to try to change the protocol, right? If ever going to happen in maybe years, right? But for us, you can just code it. You don't have to wait for the protocol developers, to agree with you or whatever. Give a very concrete example. I just we talk about the zero knowledge hackathon a little bit. So basically, a guy, who's a winner actually, run the first place in the hackathon. So basically, he implement this new curve. Okay, so I just talked about the BN curve. This is the BRS. We don't have to know all the detail, but this is another elliptic curve. Basically, is a better version, the new version of the old one, the BN curve, and it's actually being upgraded for Zcash. Zcash at the beginning using this old curve, and now they upgrade to this curve. But here's the thing, right? For Zcash, you need to have breaking changes and take them like years to upgrade. For us, you can just code it. It's like any other program, right? You can just code it, and if you are very good, maybe a day. If you're not very familiar, maybe you can do it in a week, right? So this is, you can just code it, and then everything you can just use the latest curve. You are ready to go. Okay. So hopefully, yeah, this is the proof. Yeah, you can also, this is also the circuit. You can also think, oh, this is using some other tools, not Socrates. But we don't have to go to the detail. The short out, I just want to get you the idea is, because it's a programmable, scalable and programmable, you can lot of time. You don't have to have breaking changes to add some new curve or new zero knowledge. You can just code it. Okay, you don't have to bake it, add a new opcode, or even change the consensus at the consensus layer, which Zcash has to do, just to upgrade the curve, right? So that means you can do any type of zero knowledge you want. You don't have to ask for anybody's commitment. You can just code it today, and it runs at very low cost. Okay. So not only because of this tool, you can implement anything. any zero kind of zero knowledge versus other blockchains usually is hard coded into one or maybe two zero type of zero knowledge proof. For here, we can use anything. Okay. And the last point I want to emphasize is, and because the zero knowledge, right, this algorithm is, blockchain agnostic. So whatever other blockchains can run, you can actually port it very easily. Here, you can even use the same circuit, right? Because same program, right? As for example, the factorization we've seen before, it's the same circuit. You can run on Ethereum, or you may on some other, smart contract capable or so-called zero knowledge capable blockchain. But then, once you have that circuit, you can take off them and then put it on Bitcoin. Actually, you don't have to change any of the circuit here. You can just run the process we have seen before using Socrates, and then everything that can be converted to Bitcoin instantly. So it's very portable to if you want to migrate from other blockchains. Okay. So given all the three, I would say, if you are playing with zero knowledge proof on any blockchain, so actually the Bitcoin is the most performant and most friendly zero knowledge proof. You can play with anything you want here. Okay. So that's why I think zero knowledge is going to be, for me, I'm very bullish on Bitcoin. It enables entirely new types of apps that's impossible before. Okay. And because it's very performant, you can run pretty much whatever the blockchain, you can always port it to Bitcoin. It's very easy. Okay. Any question here? Comments? Okay.
That's really good.
If not,
Thanks for doing the tutorial.
Yeah, that'd be a great first step. To just final slide I want to show you just for you to take away. So you don't have to know all the details here, but the high level idea is that different variants of zero knowledge proof, right? So we just showed you ZK Snark. ZK Snark. You maybe heard of bulletproof. Anybody heard about this thing? Bulletproof. BTC people sometimes talk about it, and also Monero people. Bulletproof basically is another way to do zero knowledge proof. You may also heard about, instead of snark, the N is non-interactive. You may heard of a stack, transparent. Okay, but we don't have to get into the basic idea is you have different ways to do zero knowledge. Okay, Snark, we just talked about one, and then you have a different metrics. The basic idea is they all have different trade-offs. Okay, so for example, some of them, the proof size is very small, and some of them is not that small. ZK Snark, the proof size usually is like it's just 200 bytes versus, let's say, Stack, it can be like 45 kilobytes, right? So it's like like 100 times or 200 times bigger, right? But then you have some other, you don't have that so-called trust setup, right? So the high level idea is you have different ways to do zero knowledge, and they all come up with their own pros and cons. So a lot of time you have to, based on your application, you have to choose between them for different trade-offs you want to have, right? Because you may have different priorities, right? For example, I want to have the smallest proof size, or you say I don't trust whoever doing the setup. I want to no trust setup. Then you go to Stack. The basic idea is you have different ways, and because zero knowledge usually is considered a very heavy cryptography. The computation is very complex. So for most, if not all other blockchains, they have to settle with one, right? For example, hey, Ethereum, let's hard code this opcode so we can support Snark. For, let's say, Monero, let's bake bulletproof at the base layer. And once you are in, you are pretty much locked in. You cannot switch, right? But for us, the good thing is it's all implemented on not in layer one, right? you always can implement this in a smart contract level. So that means you can do anything, based on your needs, right? You can choose anything you want. You're not locking as pretty much every other blockchain. Okay, make sense? High level?
Yeah, makes sense.
Okay. Yeah, that's why it makes I think the most friendly. So okay, I think that's yeah. I'm not going to cover all that. I think it's almost like its own rabbit hole. If you want to get into the deep side of zero knowledge, you can have all kinds of, you know, you pretty much have its own universe. It's pretty much you can have all kinds of crazy things going on. I think I'm not going to cover today, and I think I just want to give you a high level idea. What kind of things zero knowledge can do, and how specifically how do you use it on Bitcoin. So using, for example, the Socrates, and then going through this course, and then you can know how to integrate all this, not only with your main contract, but also even hook up with the front end, so people can actually use your apps enabled, powered by zero knowledge, and it's the best, supported best blockchain in terms of zero knowledge proof support. Okay, so I really want you to go, from here and then think about, whenever you think about problem in terms of the privacy and you want to hide something on chain, but then you can still somehow make sure nobody can cheat, you can always come back and think of zero knowledge. Okay, cool.
Yeah, thanks.
Yes.
Very good.
One question on my side. I remember when I was checking the training for the battleship,
Okay.
there was Socrates, as you mentioned, is Pythonish, but there also was a second mechanism that was like JavaScript.
Oh yes, good, good, yeah, good observation. So I just mentioned, right? So you can use, you know, there are several tools you can choose from when you are doing, let's say, ZK Snark. One is called Socrates. This is one, yeah, I like, but that's another one is also very popular. There are several others, but this is a tool we support so far. It's called Snark.js. So this is also like a tool, that you can pretty much do zero knowledge, ZK Snark. So I just want to get a sense. So this is what it looks like here. This, this is called Circom. This is its own language. So for anybody who has been into the hardware, this is pretty much like almost close to the metal. So it's very, so it's kind of like a low level, even low level than Socrates. That's why today I don't want to scare you off. But basically, the idea is if you want to do the same thing here, factorization, right? So instead of the Python-ish, this is actually what you want. So it's actually very close to the hardware circuit. So you have inputs, you have outputs, and then you connect all the wires. So that's how you do it. I think for a simple example, it looks okay, but just for me, just personally, I kind of like even the socket is a little bit more high level, I would say. But this one, a lot of people use it. There are a lot of libraries people have built using it. It's also a very popular option too. So if you want to use it, yeah, we support both. So it doesn't matter which one you choose. Make sense? It's the same thing here, the compile and the setup, calculate witness, generate proof, export, and then verify the proof there. Okay. Yeah, you can use the same. It's functional equivalent, but just I think it's Circom is a little bit low level because you are dealing with actual circuit, and then Socrates is a little bit more high level. I would say close to like Python. This one, for anybody who know the hardware language, it's like HDL. So it's a hardware description language. Yeah. So basically, you are connecting all the wires. But functionally, they are equivalent. You can do whatever you choose. You can one is, but so So if you use this, the circum is a language, what is it called, like a higher language, but also coming with a JavaScript library. You can pretty much, it's a tool set. You can integrate circum circuit. Okay.
Yeah. Thanks.
Nice. Yeah, strongly recommend you. You know, seems some of you have already, you know, started this. It's very good. Yeah. All right. Any other final remarks? All right. Let's stop here, and I hope to see all of you next week then. Okay. Have a good one.
What?
Very
Yeah,
good.
sorry, what?
Okay. Bye-bye. Go ahead.
Bye-bye. Thanks.
Thank
Bye-bye.
you. Bye.
Thank you, Chris. Bye. Have a good night.
You're welcome. Good night.
Good night.